In previous chapters, we talked about making inferences about a population parameter um, based off a sample. This idea of inferencing two samples is very, very similar. Just the only difference, the only change we're making is now we're taking two samples from the same population and we're comparing those samples. The first idea is we're going to be comparing two proportions. So we all have very similar formulas. We have a confidence interval, we have z-scores, we have error analysis, all dealing with the same idea. So the setups can be very similar. It's just now we're introducing the idea of differences. So we have here our setup for making our confidence intervals, where we take two samples of a population, our first proportion and our second proportion, and we're calculating the difference between those two proportions. To find our estimated error, the same setup as before. We have our critical value for the z-score, multiplied times the square root of our first proportion, our p hat, and our q hat, which is just 1 minus p1, and our p2 proportion, so our second proportion, and our q2 proportion, and divided by our respective sample sizes. We take that e, subtract it to our difference, add it to our difference, and that gives us a interval depending on the size, 95%, 99%, so on and so forth. When you're calculating your null hypothesis and alternate hypothesis, the null is usually going to be, the difference will be 0, meaning the two proportions will be the same. So if they are the same, that's what we're looking for, I guess. Yeah, so that's the setup for confidence intervals. Our test statistic, since we're dealing with proportions, is going to be a z-score. So same setup as before, except now we're going to be introducing differences. That's the common theme for two sample testing. Our p hat, our p1 hat minus our p2 hat. This is the thing we are testing, subtracted from our population proportion, which usually 9 times out of 10, this value will be 0, meaning the two proportions are the same. The main difference here is our idea of p bar. Our p bar is our successes from each sample added to each other, divided by our total sample size. Okay, so this is how we calculate our z-score if we're comparing two proportions of a population. The p-value, that's usually given by technology, but if you don't have technology available, you can use the table A2, which is your z-score table. And again, critical values is given by the same table, our z-score table. Okay, the next idea after comparing two proportions is the idea of comparing two means. They talk about independent means and dependent means. If the means are independent, that basically means the standard deviations are different. But it's going to be very similar. Our confidence interval is set up the same way, except now we're taking the difference of the two sample means, and we're adding in and subtracting an error. The error is found a very similar way, except now we're just adjusting the formula a little bit to account for two different samples. Remember, if we're estimating a sample mean or estimating a population mean, we use a t-score because the z-score uses the mean and a t-score does not use the mean. Okay, so that's how we set up our confidence intervals. Depending on your size of the confidence interval will change your critical value of t. If you're not setting up a confidence interval, you're just using a t-score, our test statistic, this is how we would find our t. It would be the difference of our sample means subtracted from your population mean, your two population means, which usually this value will be 0 because they want the means to be equal to each other, divided by our two different standard deviations squared, which is our variance, divided by our sample size, respectively. Okay, so again, this is our test statistic for estimating a population mean. You would use that test statistic to find the area to the right of the curve, and that will give you your p-value, and so on and so forth. If you want to find your p-value, that can be given by technology or by using the t-score table if technology is not present. And all those will help you reject or accept the null hypothesis. This is all basically the same idea as hypothesis testing, except now we're just introducing more than one sample. So the concepts are the same. The only thing that's changing is the formulas. Again, the concepts are the same, just the formulas are changing. So we calculated the two samples for our two means, which were independent, which were the standard deviation was the same. And then we can also calculate when the two means are dependent, meaning that standard deviations are going to be the same. Confidence intervals can be a little different, but it's the same idea. We have D bar, which represents the differences between the means. So you're going to have a paired sample. So all the data points are going to be paired with another data point. You're going to find a difference between those data points, and then you're going to add up those differences, find the average. That's going to be D bar. So we have our sample mean average, subtract the error, add the error, and that gives you a confidence interval. Since we are estimating a population mean, we're using a t-score again. Depending on the size of the confidence interval, your critical value will be different. So same formula, just different usage. The t-score, since we're dealing with mean, we're going to be doing a t-score. We have our difference average minus your population mean of differences, divided by the standard deviation, divided by the square root of the sample size. And again, the p-value will be given by technology or by the table, the t-table, if technology is not present. And the critical values are given by the t-table. Okay, so it's the same concepts as hypothesis testing. Just the only difference is the formulas changed a little bit, but the analysis is the same, whether reject the null or fail to reject the null. All those processes are the same.